Good afternoon, everyone. Today we will speak about our results for Google Summer Code. You know that Radare is currently participating in Google Summer of Code and also making our own Radare Summer of Code. What's an important part is that we participated for almost 4 years. First we were declined and we started our own Radare Summer of Code. And with the gathered experience, we managed to get inside the Google Summer of Code as well. But also we kept making our own Summer of Code still. And today we will speak about results of 3 projects which were accepted and successfully finished. And if you remember from the previous talk about Windows support and WinDBG using with Radare and using GDB protocol inside Radare, this is highly related to the talks which will be next. And so I encourage you to welcome our 3 students. The first talk will be from Antide Petit about Windows platform support. And this is a talk about his work on improving the Windows support. Even before Radare was able to work on the Windows, we usually compiled it using MinGV and Cygwin. But before, it wasn't very stable like we wanted to. So Antide made a very good job on porting it for MSVS. So you can basically even develop and debug Radare using Visual Studio. And also he worked on improving debugging support in Windows, including some improvements to WinDBG protocol. And after that, you will see the talks from 2 students who worked on debuggers features. The first will be Shimant Baroa about implementing GDB server inside Radare. So you can make a small GDB server and copy it on a target and connect using Radare, using GDB protocol. And moreover, which is very important, he fixed a lot of bugs and improved overall the support of GDB protocol. So now Radare is able to connect to GDB and LLDB and so on. And very unique feature for tools like Radare is reverse debugging. Ren Kimura will talk you about his results in improving reversible debugging. Many of you heard of projects like RR from Mozilla or Kira from GeoHot. And the problem is that RR is targeting the source level debugging. So despite it has a very good support for reversible debugging, Radare is only one tool which is targeting reversible debugging for binary files without sources. And also, very unique feature, it's supporting reversible debugging using emulation issue. If someone, if some of you were on our trainings, you saw a few examples how to use reversible debugging for recording the tracing and backstepping. Thank you, and I will give a word to Antide.
Thank you. So, hi everybody. So, I'm Antide Petit, also known as Xarkis on GitHub or Twitter. So, I'm going to say a bit about me. So, I'm a French student, currently studying in NCMAG, Grenoble. Usually, I enjoy playing CTF on my spare time. And also, I'm a member of a GreeHack organization, which is a conference in Grenoble too, talking about IT security. And if you don't know what to do this November, you're welcome. So, how I joined this Summer of Code? Actually, I was often using r2 during capture the flags. During capture the flags, especially when doing reverse engineering and exploiting. And so I had already contributed a bit before, like I first introduced SWF support, disassembly support, and it seemed nice to do it again, especially when you have a full summer of time. So my choice was on MSVC support because, well, it's 2017, and just give me one good reason not to have a cross-platform software. I see none. It's not hard to port something from Linux to Windows. Just takes some time and some slave students. So my first try was doing it using CCCL, because currently r2 can be compiled with a lot of makes files and GCC. And basically CCCL is a wrapper around GCC, which translates any GCC command to cl.exit, cl, which is the MSVC compiler. So it's translated like a -o into /out extra. So it was a first try, but still you required MinGW to use it because it was still bash compliant. So I was not 100% satisfied with that. And then we came using the Mason build system, which I will explain a bit later. And most of Windows specific things were already done from MinGW, like threads handling, forking, etc. And so there were many hundreds of files having GCC specific preprocessors, and it was a lot of translation to being able to compile r2 onto MSVC. And so now you can download the builds who work from Windows XP to Windows 10. So to compile r2 on Windows as of today, you only need Python with the Mason build system. So it's a build system written in Python, and and it relies on Ninja, which is another build system, or MS Build or anything else. So to compile it, you just go in your r2 folder and press mason.bat, and it will compile it. So let's have a look. Oh, come on. So, okay, can you see? Yeah, that's fine. So I guess I'm in my r2. So, as I was saying, there's a mason.bat file which contains everything required to compile r2 using Mason, whatever. So I can just start it, and doing so, it will use the Ninja bin system and compile everything from scratch and asking nothing. So it's going to take a long time, so I'm going to stop there. But you can also use it to generate a Visual Studio project file, which is very handy. So you just type mason.bat-p, and this way it's going to create a Visual Studio project, which we can see here in my build 1, 2, 3 folder. And so it creates everything required and for every library of r2 extra. So I already made it because it takes quite a lot of time to compile r2. So if it works, we might be able to debug it on live using Visual Studio. If not, then it's a shame. Yeah. Maybe it will wake up someday. But basically, as you can see on the right, I have all access to every r2 file, and you can develop r2, compile and debug it using the whole Microsoft tools. So it's very nice for any Windows developer. So another part of this GSoC was to deal with DLL debugging. It was planned, but we discussed a lot about the way to implement it. So for now, you're not able to directly debug a DLL, but we use a trick using r2con, so you are able to run a specific function of a DLL. So if we can just have a small example. Where am I? Here. So r2con, you can use r2con to ask him to run a library. It's cross-platform, so you can do it on OS X and Linux too. So you just set the parameter runlib to whatever library you like to run. So in my case, I'm going to run user32.dll, and also you can pass it the function you want to run. So for example, message box A, and then you pass the arguments one by one. So the first one, I'm going to give him null. Second one, I can say some title, and I think it's reverse actually, body, title, and arg4, you can give it any integer you like. And so it's calling the function directly in the library. So we're not able yet to debug it. If you still want to do it, you can debug r2 and calling it like this and putting the breakpoint at the correct place. It's working, but not very handful. So there's just a bit of work to finish this, but everything is there. Also, I worked on PDB support. So you can now use IDP to load information of PDB file, IDPD to download the PDB file if available, and this one, if you're familiar with r2 commands, the star is used to verbose into r2 commands, and the dot at first is used to execute those commands. So we can have a quick example, I guess. Yeah. For instance, sorry. So for instance, like I can load my user32.dll. So as you can see, it has a dbg file and also a UID, and you can use IDPD to download the available, the correct PDB file. I guess it's just check the options around PDB. You have to set PDB server. It's already set to the Microsoft one extra, so you don't have to do much thing. But this can be customized very easily, and so you can directly use IDP. So demo effect. Oh, wait. Yeah, so you can use IDP, and it's showing you every debugging information related to this file. And so using, as you can see, I have some imports, and if I use .idp star, it's going to load all of them. And so I came from 800 symbols to 4,000. So it's quite handy to use them while reversing Windows applications. Also, another big work is using tests on Windows. So currently there's a test suite for r2 Linux and also on OS X, which is run on Travis, and it's based on Makefiles extra. So we added Windows to AppVeyor, so it's compiled every day, but it's compiled actually at every pull request, but there's no test running as of today. So we started to translate those tests to a new test suite, which is based on Node.js, and it's much faster, and it's cross-platform, so you're not stuck using it on Unix. Actually we had to try with MinGW, but again it's very slow, so we couldn't use it, and AppVeyor has a 1 hour maximum time of a test, so doesn't work. So there's a pending pull request about this, which I hope I will merge in a few days, next day. Another interesting thing is the Windows installer. So we made a Windows installer. There's no administrative rights required, and it adds right-click context, and it's about 8 megabytes, so it's quite pretty small. So I am going to show you. So I downloaded. There's no official link for now, but you can go on the r2con GitHub, and if you scroll down a bit, there's the AppWare build status, and here it's passing. So if you click on it, you come to a nice page like this, showing the different jobs that we have: Visual Studio, MinGW, etc. So if you click on the first one, you'll be welcomed with another page like this, and the installer is in the artifacts page. And again, you can download it from here. So as you can see, it's 8 megabytes. Otherwise, you can download the whole r2 stuff. So I'm just going to launch it. So it's asking for language, license, destination, etc. We don't care. And it's done. And it's very easy. And now you can right-click on any binary you like. And it asks you to open it in r2. And so now I just open my ninja.exe with a simple right-click, like any Windows user would do. So that's it for the installer. Another interesting feature I did implement was the I/O plugin for AR or lib files. So you can load any file within an archive. So if you don't know AR or lib files, it's basically a very simple archive system which contains usually objects files to use during compilation, or in any static library, whatever. So the purpose of this was to massively open Windows lib files to generate signatures. And so with those signatures, we would be able to have every symbol during reversing any Windows binary. So again, we can have a look. I don't know, any .a would just do it. So shr ar lib ar.a. AR.o. So I'm asking to open the AR.o, which is contained in the libr.ar.a file, and it's showing me every information. The offset is dependent on the AR.o file, not file. It's working nice. So with this, we can simply call a signatures function to generate them, and then we can automatically do it on every lib file, and it's going to be much faster. All right, so now I also tried improving the support of WinDBG. We talked about it a little bit earlier. So there was already a WinDBG implementation on r2, but it was not. When I tried it, it was not working, and when I fixed it, it was not correctly fixed, so I had to do a bit of work on it. Currently it's not properly working, but reversing the whole KDE protocol could not fit into this GSoC, especially when you start in August. So maybe someone will do it someday, but for now there are many stuff to improve. Well, yes, so a quick demo about using Visual Studio. If you're not familiar with it, you can, for instance, I put a breakpoint on the CMD section, and I just called the section command, and then pressing F11, you can just step through the code, and it's very handy for debugging. Well, any Windows developer uses this, I guess. So that's it. So the WinDBG plugins allows me to debug any KDE enabled Windows machine using here actually it's using a serial pipe. There's no network protocol supported for now, but if anyone wants to do it, please do. So for now I'm using a serial pipe through my VM, and oh, sorry, forgot to tell debug. Okay, I just broke it. No? Oh. Okay, demo effect. Annoying. Maybe I'm going to try again because I don't want to fail on this. So yeah, we have a lot of fun during this GSoC because waiting was like 50% of my time. Oh, come on. I know, I just updated from Git before the talk, and I think someone broke it because of SIL merge. Thank you, Conrad. So sorry about this, I'm not going to show you. So there's still a lot of remaining work. The most important is to translate the whole test suite to the node 1. So it will have faster testing on Linux and also testing at all on Windows. We also have to improve signatures and PDB support because PDB works, but some files are sometimes a bit broken or generate warnings. So we still have to work on this. And I guess you no more have excuses to use R2 on Windows. If you do, tell me. Everything is documented, so if you still don't know about this, I think many people say it again and again, but you can use the Radar-E2 book, just Google Radar-E2 book, and there's also some documentation in the Radar-E2 master tree. Also, you can ask on a Radar-E2 Freenode and Telegram channels. Oh yeah, forgot this one. I also like to thank my mentors, Xulka and Meijin over there, and also Pancake and many others like squatters and people who helped me during this GSoC. And if you have any question, please do ask.
Nobody? Okay.
Thanks. Or just switch to Windows Enter.
Yeah, this is not my laptop, so I won't be that efficient. But then, yeah. Hi, I'm Srimant Barwa. I am from India, a computer science student, and interested in systems programming, reverse engineering. Kernel development and stuff like that. But then, yeah, there are two interests me because of that. For GSoC 17, I worked on improving GDB support inside Radar. There was existing GDB support, but when I tried it, it didn't work, it didn't connect. The original proposal, which they put up on the list of ideas, was to implement a GDB server inside Radar, and that has sort of been done. But I focus more on improving the GDB client because I guess that is what most users will use. And I implemented a lot of stuff which I'll talk about. A lot of my time throughout GSoC was spent, fixing bugs which were unexpected because, and they kept popping up because, based on different users' complaints. And yeah, my mentors for GSoC were Pancake and Isvika. And I would also thank Myjin, Naitaman, Vijay, r2con, Finyo, and other people who helped me. Yeah, let's get on to it. So I implemented GDB server inside Radar. That was the first thing I did. Yeah, you sort of started with, as Pancake talked in the morning, you have equal to sign for all your remote commands. And there's a subcommand inside it which starts GDB server inside Radar. And I will not be talking in detail about this because it is sort of broken, as in memories are broken because of, I guess, the SAR will merge and it'll be fixed soon. But then, yeah, it is quite buggy. I'll focus more on the GDB client implementation, which I sort of worked out, and the existing GDB implementation had you connecting. So GDB is basically debug backend, and that's implemented as an IO plugin. And for all your IO plugins, you have this sort of prefix which you use to select what you're going to open. So tag D to signify as a debugger, and then GDB and host port. And most normal options work, -A for setting architecture, -B for bits, stuff like that. And you can debug normally like you would any normal debugger. And let's see. Okay, so let's see. Okay, let's just debug the data. And okay. So you sort of open radar as you would, and you in step you can continue and stuff. So yeah, sort of works. I mean, it works. And so it's like you would use a normal debugger in radar. What's new? So those who've used remote debugging over GDB, they will know that GDB implements monitor commands. So monitor commands are basically, GDB basically defines just a protocol. It did not, and they have a sample implementation of GDB server, but they have a protocol which GDB servers need to implement. So different backends, different GDB servers can implement commands which are not included within the protocol. So like QEMU has different options, your standard GDB server has different options. So those are included within monitor commands. Now when you have your normal GDB server, you can look at monitor commands with monitor, and then send whatever set, and that enables protocol debugging, where you can debug the protocol messages, but yeah, so on. So it probably will be more useful to people who need the specific functionality for the GDB server. And yeah, so this was mentioned, I think Svilka mentioned it in the initial training. So what was happening was we noticed a lot of AVR targets were crashing when you connected with radar, and we figured out that it was because something like SimAVR does not support a packet size which was being done by normal radar, and so we had to figure out how to limit the packet size. Now some GDB servers report a packet size, but SimAVR does not, so we had to specify some standard sizes and which could be configured. And so yeah, you can set the packet size. By the way, if you don't know, equal to an exclamation, that is channel into the IO system. So all your IO backends, they implement certain commands to this IO system. So the setting and getting of the current packet size is implemented through the IO system. And you can also set an environment variable to set the max packet size when you're connecting, so that your initial connection does not segfault the target. And yeah, so you can this wasn't working. The list of threads and then the current active thread, switching threads, and right now I don't know if we have. Okay, so this will work more with something like Camo. Where will I be? Yeah. So okay. In Camo, if anyone's used, yeah. So what Camo does for some targets is implements. When you have a SMP system, it implements different cores as threads. So that's where that's because it's because of that I implemented. Came across the idea of implementing this. So you can switch threads, switch cores with radar like you would normally do. That probably I'll show in the Camo demo. XML target description. So GDB recognizes that a lot of targets, even if it's ARM or MIPS, there are subtle differences between all targets. So targets can specify, their own special configurations, registers, flags in XML format, and certain GDB servers can send that. They have to report support. So if the GDB server supports it, then I can pass it into the radar register profile, and so you can use the target. Process memory maps wasn't supported. I sort of added that. All your DM commands, DMH for heap inspection and stuff like that, all that has been done. If the GDB server supports it, obviously some GDB servers don't, and get the file name which was executed. So basically when you're opening a connection with radar, you're just connecting to a GDB target. For a lot of stuff you might need to know which was the file that you executed. So again, subject to support from the GDB server, you can get the executed file name from the target. And also there was a complaint, there were multiple complaints about how the GDB debugging was slow. So we added improvements. Common complaint was that we were reading registers, for every memory read we had to run 3 register reads of the same thing even though it wasn't changing. So register caching, and certain GDB servers have no ACK mode because you're communicating over TCP anyway, so why would you need an ACK? So no ACK mode, that's probably used back in the day when GDB server was done over serial. So no ACK mode is supported right now, and yeah, you can kill the target, detach from the target. Let's see. So again, detach is implemented inside the IO system. So just detach, and your remote will run, I guess. Did not, but then okay, yeah, basically detached, and that helps a lot when you're debugging a remote, let's say using Camo to debug a kernel or something like that. And killing, kill signals are supported as radar would do it. And yeah, so this. Now when we debug locally, it's okay to expect symbols to be loaded, and to have a lot of symbols, sections, but those are loaded from your ELF binary. When you're debugging remotely, you sometimes do not have, the GDB server does not know the ELF binary. So this is basically done by 2 different parts of radar. The GDB connection, reading all your memory maps, that's done by the IO plugin or the debug plugin, and getting binary information like symbols, etc., is done by the bin plugin. So and those are not really connected. So a lot of the stuff that getting the memory maps, getting the name of the executed file led up to automatically loading symbols from the binary. And so yeah, right now when we can when we connect with GDB localhost something, it automatically gets the remote file which is executed, and if it is present locally, it will load symbols from the local file. And so you can do something like continue until sim main, and that will work when normally earlier did not, because you have the main symbol loaded right now. And this, so sometimes you might not have the image present locally, and let's say you're debugging again a kernel. So let's yeah, and okay, this is converts crack me, but then how I have no idea how this works, right? So right now the binary is not present locally on the same path as on the kernel, because obviously it's not present on the path it's loaded as the kernel. So we can specify the path to the binary by this config variable which we cooked up, dbg exe path, and let's say it is, I guess, if I'm not wrong, probably. And you have to specify the base address by which the base symbols, obviously, because sometimes the GDB server, they boast this when you read the memory maps. Camo doesn't let you read memory maps, so you have to specify the base address manually to the base symbols, and you can do that. So hopefully this works. Do we have symbols? We have sections at least, yeah. So the kernel's sections, all this has been read from the kernel binary. So if you had symbols in the, this binary is probably stripped. If you had symbols in the binary, you would be able to read them too, and be able to debug using those symbols. So you can have, I guess, entry 0 is reported. So yeah, loading of symbols has been done, and that's pretty much it in terms of what I've implemented this time. And yeah, challenges I faced. Of course, Radar has a huge code base. I think it's around 700k lines of code, more than that. And GDB protocol. So the protocol description I was reading was from 2008, and it hadn't been updated. And a lot of stuff was, as you know, to do or not really specified. So I had to go through packet catches and read out, parse them to see what was going on. And yeah, documentation exists, but it's not the best. And register profile parsing, because so even in the XML target description I was talking about, you do not have really much clarity about what the specific registers are. Like, let's say your instruction pointer is reported, but your stack pointer, base pointer, they're not really clear from the XML description, so you have to add them sort of manually to your register profile, and that's something we have to work on, but then that's, yeah, challenges as now. So yeah, that's it from me. Thank you, I guess. Any questions, if any? No? No? Okay. That's it. Yeah. Okay.
Okay. Hi. Thank you for inviting. I'm Ren Kimura. I'm from Japan, and today I'm not gonna talk about reverse debugging with r2, and it's my this year's GSoC work. And firstly, I'll give a brief self-introduction. And I am a computer science master course at the Kobe University in Japan, and especially interested in kernel exploitation. And I've contributed to r2 in this year's GSoC. So thanks a lot my mentors and r2 community for helping my works. By the way, there are some cool Japanese words in r2 related project like iaito and kaitai, so that's cool. Okay, so in this presentation, I would like to demonstrate my GSoC works. So my project main goal is add reversing debugging support to r2. So reverse debugging is the ability to make the program being debugged step and continue in reverse. In short, using this ability, you can seek program counter backward. Okay, so for example, it's a simple program, hello world program, and if program counter is now at 40053F, and you can step back one by one to 53A, 537, and 536. So in reverse. Okay, but how can I restore previous program state? So in this program, you should restore some registers. So for example, at 40053A, EDI register has assigned hello world address. But when after you step back, EDI register must be restored to previous value. So how can I do this? Okay, so there are some approaches to implement reverse debugging, and mainly there are timeless debugging and record and replay. So these concepts are very similar, but a bit different. So let's see more detail. And firstly, I'll explain about timeless debugging proposed by George Hotz last year. And it records all operations like load store to memory or registers. So all state is tracked while a program is running, and so you can debug in the past. So Killer is timeless debugger developed by George Hotz himself and uses QEMU for this tracing. But of course, however, this approach is not suitable for Radio 2 because it requires emulator or, yeah. So I'll focus on another approach, record and replay. And as the name suggests, it records entire program state at some point and replay from it to desired point, right? So, for example, you are now at 40053F address, and you can single step back from current address to 40053A by replaying from more previous address, like 40056 to 40053A. So replay until previous address. Okay, so it's quite simple. So in GSoC term, firstly I've added a simple r2 recording command like DTS, and that can save program state at any point. So in R2, I've named trace session. I've named this record as trace session. Okay, so you can see more detail by typing DTS question mark in your debugger console. So okay, to run reverse debugging command, firstly you need to record initial program state by DTS plus. And then And you can step or continue as usual and go forward to 40053F, for example. And now you are ready to go backward by reverse debugging command. And let's back one step by DSB, debug step back command, from 40053F to 553A. So when execute DSB command, R2 internally restores program state, including memory and register to previous trace session saved before. And of course, program counter register is also set to previous address 400536. So all program state has migrated. Okay. So next, R2 replay program until 40053A. So as a result, program counter seems to be step 1 backed from 53F to 53A. Okay. And moreover, not only step back, but also you can do continue back by DCV command that seeks program counter backward until hits a breakpoint. Okay, I'll show you a demo of these commands. Change that. I want to launch the arts command line. Okay, thank you. Okay. Sorry. Okay, so now debugging bin errors and debug continue to main and and you are now at 40. Can you see that? 4028B0. Okay. And so a comment. Keyboard layout is a bit different. Okay, sorry. And so now, where is plus? Okay. So now we should record program state by DTS plus command. So and so your get R2 has saved one session at 4028B0. Okay, so this saved session and okay. And okay, so and go forward and 10 DSO by 10 TSO, and you are now at 402867. And then next, let's try the debug step. Debug one step back. Okay. So you run DSB. Okay. So your program counter is step back one. So you are now at 286C3, and okay. So and again. 28VF. And again and again. So step back. Okay, and you are now at 28B to 8B9. Okay, so you can do step back command by DSB, and there are another function called debug continue back. So so again, I try to okay, so I've set a breakpoint at 28B0, okay, and go forward, and so let's run the debug continue back DCB command, okay. Oops, oh, sorry, I forgot to save trace session. Oh, that's work. Okay. Yeah, it's okay. And okay, so debug continue back. Yeah, okay. So let's see. Yeah, okay. So program counter has bugged until hit the breakpoint. Okay, so now program counter has bugged to 28B0 that has set breakpoint. Okay, so okay, so I'll show the simple reverse debugging command, but yeah, of course, when you reverse debug commands at several times, R2 always replay from previous trace session, okay, and so it can be waste of execution time, especially some heavy operations like long loop iteration or memory copying are critical for replay. So I added some performance optimizations. So first one is checkpoint system. So when R2 replaying some trace sessions are automatically saved as a checkpoint. So from the next time, R2 can replay from nearest one. So it quite fast. But it comes up against memory size problem. Okay. So there are many trace sessions saved as checkpoint automatically or manually by user. So TTS plus command, and each trace session has entire program state like all memory and register dump. So I added diff style trace session format, and each session has only changed the memory paths from previous trace session, so it reduces total session size dramatically. For example, there are 3 trace sessions, and the first one has an entire memory dump, but second and third one have only changed the pages from previous one. So before, each session has entire dump, but after each session have only changed pages. Oh. Oh. That's a bit difficult. Okay, and so, and I show demo. So previously I've saved as one session, a session 0, and so for the forwarding, and now so I save another new trace session by DTS plus, okay, and oh, so wait. Okay. So I saved 3 sessions now, and session 0 have entire memory dump, but session 2 only have changed pages from previous session 1. So for example, 65F000 to 6200 area in this area, page number 0 is changed. So so this page is only saved at session 2. Okay, so session 2 has only saved these pages. So okay. So diff style optimization. Okay. So okay, finally, not only debugger mode, but you can also do reversing debugging for ECL mode. Okay. ECL is powerful intermediate language used by R2, as you know, and there are some applications for this feature, like code emulation and decompiling and VM emulation. So, core logic of ECL reverse debugger is same as of native debugger. So it recalls ECL stack memory area and reperform it, and so you can use ATS plus command to record ECL state and AESV to step 1 back in ECL mode. Okay, so I'll show final demo. Which is equal. Okay. So sorry. And okay. Yeah. Okay, so in easy mode, it's in easy mode, and so you can easy program state by AETS plus command. Okay, and seek program counter to afford. So now you are now at 4054, and AESB, yeah, you can, your counter is step back to 1. So you are now at 404B. Yeah, and so on, okay? So you can debug reverse in ECM mode. Okay. Okay, so during GSoC time, I added a basic reverse debugging ability to r2, but there are still some works. Currently, r2 reverse debugger is not supporting non-deterministic events like syscall, signal handling, and timer function, for example. And these events must be recorded and replayed correctly too. So I'm gonna continue to work after GSoC has been finished. Okay. Thank you. So does anyone have a question? I'm not good at English, but I'll try asking the question as soon as possible. So does anyone?
If you want to have 2 sessions in a loop, for example, how does you go back to the session of the previous iteration? How you handle it well, or there's some kind of special command or something?
So wrong. Yeah. So first time, also replayer run wrong group iteration, but during the execution, replayer put trace sessions automatically during wrong group iteration. So next time you can replay from end of wrong group iteration. So it first, so it not need to replay from head of wrong group iteration. So okay, that's right. So sorry.
When the ether was designed, it was designed so that you can overwrite these operations. Did you think about overwriting every operation in the ether so that you just track what actually happens, and then you can just read at the memory locations and the registers so that you just build tiny chains of the things that actually change? So in that case, you could just create revert operations for the thing, and I think you could save lots of memory and do it much faster. I think you could even do this in debugger if you just create operations that do not write and just trace the thing that will going to happen before you before you do the single step, and then later just create some kind of stack where you push all the stuff and then just pop it back again so that you just step revert instead of just dumping the memory all the time. Did you think about it? And if so, did you have a good reason to not follow that approach?
Oh, sorry. It's not. What is the question? So sorry. Sorry.
The basic thing is that ether is designed so that you can redefine the operations that the ether does. It's all based on callbacks in a hash table.
Yeah.
So you can basically define operations that do not operate and only track what is going to happen, and then just track compute a new value and compute an old value, and then you can store the old value and create an invert operation of that what is going to happen next. And if you use that technique, I think you can save lots of memory, lots of time, and you can just step backwards by just redefining the ether operations, and you can even do this when you are debugging. and not just running things in easel. Did you think about this? And if did you have a good reason to not follow that approach?
Yeah, I think that's good idea. So, okay, so I try to implement these ideas. So, could you tell me more detail after presentation? Okay, thank you.
So, one of the problems that you have with this is that SEAL doesn't implement all the instructions. And using the way that he did is that you can handle everything, like maybe if there is an instruction that is not properly handled by a SEAL, or it's having some kind of side effect that you are not expecting because there is another threat, something that you're not handling properly, it will not work. But it's correct that if a SEAL works correctly in all the situations, it will work better because you can have like some kind of memory structure that stores all the events that are happening in every SEAL instruction, or it could be even possible to reverse the SEAL expression to have some kind of inverted operation. So you have some kind of reverse disassembly that will be executing that. But yeah, that was another way for implementing that, but it's having some restrictions mainly imposed by SEAL. Yeah. Anyone else? Nope.
I have a couple more words about Google Summer of Code. I want to say thanks again to our participants at first, and I want to remind you that of course we are going to join Google Summer of Code, and most probably we are going to continue our own Summer of Code next year. So if you are a student and want to help Radar and want to help develop new feature, or want to do some kind of research using Radar, welcome. And starting about maybe April or so, please follow us on Twitter and blog radar.today, and you will see when we will start accepting members, potential members. So